In previous modules, we've been busy obtaining the responses of circuits that are excited by sources that has fixed frequencies. In fact, when we solve circuits using phasor analysis, we were not concerned at all uh, by the frequency of the sources. In this module, we will look at the responses of circuits with sources having variable frequencies. This topic in frequency response is or has several applications, and one of them is in filters and resonance. These will be our objectives for this module. So first we will define what we mean by frequency response. Then we'll we'll define what is a transfer function. So this is a tool used in quantifying the frequency response. We also um, covered a decibel scale and how it is used to measure the gain, uh, which is will be used in our study of the Bode plot of the frequency response. So here, let's say we have a simple RL circuit that is excited by a source with a particular frequency given by omega, and we obtain the output of that circuit across the inductor. So let's label it as V naught. By a voltage division, we can obtain the phasor voltage V naught, uh, and it is given by this one. We can convert that into a polar form, and that should give us this um, form here. So this one is the magnitude of V naught, while this is the phase of V naught. Um, then, having obtained the phasor value of V naught, we can solve for the time domain uh, voltage across the inductor, and that should give us this one. So as seen from the time domain expression, the voltage leads the input voltage by this angle owing to the positive sign of the phase angle. Uh, so having obtained the voltage, the time domain expression of the voltage across the inductor, let's say we will vary the frequency omega and observe what happens to our output voltage. So in this column, we have various uh, values for omega. So we vary it from 0 to infinity, and in between that, we have specific values in terms of the ratio R over L. So here we have 10% of R over L, R over L, 10 times R over L, and so on. Here on the second column is our V naught, and we also include the phase of V naught. So if omega is 0, uh, we can use this to obtain the magnitude, so that will yield a value of 0, um, and a phase angle of 90 degrees. So at omega equals 0, that is this input here is actually DC if our omega is 0. So that will give us no output actually, because we have a magnitude that is 0, although the phase angle is 90 degrees. Then we uh, slightly increase omega to 10% of R over L. That should give us a slight increase in magnitude, and but a slightly lower phase angle. A further increase in omega will increase the magnitude, but will decrease the phase angle. And if we do that if we continue to increase omega, the magnitude will reach a limit, or will continue to increase, but um, it will be limited up to V sub m, which is the amplitude of our input voltage, but the uh, phase angle will tend to decrease to 0. So what then is the frequency response? So as what we have shown, as we increase for the series RL, as we increase the frequency of the input source, we observe that uh, the um, the magnitude of the voltage across the inductor increases, but to a certain limit, and the phase angle is actually decreasing. So this um, brings us to frequency response. No? So that response of the circuit that we just obtained is what we get when we vary the frequency of the RL circuit, of the input voltage of the RL circuit. So we then define the frequency response as the change in behavior of the circuit with changes in the excitation or input frequency. That results to changes in responses. So here is our circuit a while ago. So we have here an input, and we vary the frequency of the input. We notice that the output varies as well, because the behavior of this network, or the RL in our example, is affected. Okay, so for RL, this is our input, and we obtain an output that is like this, which is actually a function of the frequency of the input voltage. Um, we can express this result by the input voltage. So we obtain this, and in fact, we can get the ratio of the output voltage with the input voltage, and that should give us this result at the bottom. So this one is really V naught, that is a function of the frequency divided by um, the input voltage, which is also a function of frequency. So this thing here is what we call the transfer function with respect to the output. So in our next series of videos, we'll be uh, digging deeper into frequency response, and we'll start with transfer function.